So let's take a look at the direct comparison test, or DCT. So the formula for the DCT, let's say we have the series of a sub n. We can actually compare it to a similar series, b sub n. And if b sub n, the series of b sub n, if it is convergent, and a sub n is less than or equal to b sub n, that means that the series of a sub n is also convergent. Now let's say the series of b sub n is divergent. If a sub n is greater than or equal to b sub n, then the series of a sub n is now also divergent. Now if we get that b sub n is convergent and a sub n is less than or equal to b sub n, then it's inconclusive. Or if we get that b sub n is divergent and a sub n is less than or equal to b sub n, it is also inconclusive. So in that case, you would probably have to use another test, and usually the limit comparison test would work. So it has to follow these strict rules here. So looking at number 1, we have the series from 1 to infinity of 1 over n squared plus n plus 1. Now, I can't really break the denominator up into linear factors, so I can't use the telescoping series. And I cannot do partial fraction decomposition. So looking at number 1, we have the series from 1 to infinity of 1 over n squared plus n plus 1. Now, I can't really break up the denominator and do partial fraction decomposition and use a telescoping series, but what I can do is compare it to a similar series that I know the convergence or the divergence of. Let's say n equals 1 to infinity. Now I'm just going to look at the most significant terms on the numerator and the denominator. On the numerator, we obviously have 1, and the highest degree in the denominator is n squared. So I can compare this to the series from 1 to infinity of 1 over n squared. And we know that we can use the p-test on this series. So if p equals 2 and 2 is greater than 1, we know that this specific series will converge by the p-test. So now we can compare these two series. So I'll say 1 over n squared plus n plus 1 on one side and 1 over n squared on the other. And in order to see which one's greater than the other, notice how we have the same numerator of 1, but this side is much heavier than this side, which means that 1 over n squared is greater than 1 over n squared plus n plus 1. Because you'll get a smaller number on the left side if you divide by a much larger denominator than if you divide by the smaller denominator. And the other way you can do it is by cross multiplication. So I'll get n squared on one side and then n squared plus n plus 1. Obviously the right side is greater, which means the right fraction is greater. So if we know that 1 over n squared converges the series, and 1 over n squared plus n plus 1 is smaller than 1 over n squared, anything smaller will also converge. So the series of 1 over n squared plus n plus 1 will converge by the DCT, or direct comparison test. So for number 2, we have the infinite series from 1 to infinity of n plus 1 over n squared. So to compare this to a similar term, I can look at the significant values of the numerator and the denominator. So to compare this to a similar series, I can just look at the highest degree of the numerator and the denominator. The highest degree in the numerator is n, and the highest degree in the denominator is n squared. So if I take n over n squared and simplify that, we'll just get n to the negative first, or 1 over n. So I can compare it to the series, that was a bad series sign there, of 1 over n. And obviously we know that the 1 over n is a divergent harmonic series. Or if you forgot about that, we have the p-test, so n to the first power. If p is equal to 1, less than or equal to 1, this means that the series of 1 over n diverges by the p-test, or you can write it's a divergent harmonic series. So now I can compare these two series. So I'll put these side by side. So n plus 1 over n squared, and then 1 over n. So like the previous problem, we don't have similar terms in the numerator, so we cannot just see which one is bottom heavy. But what we can do is cross multiply. So when I multiply, we'll get n squared, or n plus 1 times n, which is n squared plus n. And then on the right hand side, we'll get n squared times 1, or just n squared. Obviously the left one is bigger, which means the left fraction is bigger. So if we know that 1 over n, the series of 1 over n, diverges by the p-test, and n plus 1 over n squared is greater than this specific divergent series, this means that the series from 1 to infinity of n plus 1 over n squared diverges as well by the direct comparison test. So for number 3, we have the series from 1 to infinity of cosine squared n over n squared plus 1. So if I were to compare this to a similar series here, obviously the most significant, or the highest degree of the denominator is n squared, and the highest degree of the numerator is cosine squared n. And if you think about it, cosine of n oscillates between -1 and 1. So basically you can pick any value between those two values. But for simplicity, I'm just going to pick 1. And obviously we take it squared, and 1 squared is 1. So really I can compare this to 1 over n squared. And 1 over n squared, obviously we can use the p-test. So p equals 2. 2 is greater than 1, which means the series, this specific series, will converge by the p-test. And then to compare these two series here, we have cosine squared n over n squared plus 1, and 1 over n squared. We can just cross multiply. So on the left hand side, n squared cosine squared n, and on the right hand side, n squared plus 1 times 1, which is just still n squared plus 1. Once again, cosine of n is sort of oscillates between -1 and 1, so most of the time it's going to be a fraction under less than 1, which means it'll greatly reduce the value of n squared, which means that the right hand side is greater. So if the right hand side is greater, the right fraction is greater. And we know that 1 over n squared converges by the p-test. And cosine squared n over n squared plus 1 is a smaller value, which means that the series of cosine squared n also converges by the direct comparison test.